Hello everyone, welcome to Electrical Concepts by PAVP. Myself P. Anjaneyavara Prasad, an assistant professor from Triple Department in Jipula Reddy Engineering College. I hope all of you are doing well. In today's lecture, we are going to start one of the most important topics in electrical machines, which is DC machine. Now, before we begin, let me ask one simple question. Have you ever wondered how an electric fan, mixer grinder, electric vehicle, or water pump converts electrical energy into mechanical rotation? Or how electricity is generated in power stations before it reaches our homes? The answer lies in between electrical machines. Basically, a DC machine can work in two different modes. The first one is as a DC motor, which converts electrical energy into mechanical energy, and second one is as a DC generator, which converts mechanical energy into electrical energy. Interestingly, both DC motor and DC generator have almost same kind of construction. The only difference lies in their operating principles. So, in this today's lecture, we will understand the construction of a DC machine and function of every important part, along with working principles of both DC motor as well as DC generator. So, without wasting any time, let's begin. Here you can see the construction of a DC machine. Also, there are many components. We will understand each part one by one. But at the end of this lecture, you will know exactly why every component is used. Let's start with the outermost part, which is called yoke. You can think of yoke as a body or skeleton of the machine. Just as our body provides support to all internal organs, the yoke provides mechanical support to all internal parts of the machine. It also protects the machine from dust, moisture, external damages. Apart from providing mechanical strength, the yoke also acts as a path for magnetic flux. For small DC machines, the yoke is generally made up of cast iron because of its economical aspect. For large industrial machines, the cast steel is preferred because of its higher mechanical strength and better magnetic properties. And the next one is we have pole cores and pole shoes. They are fixed in inner side of the yoke. The main function of the pole core is support the field winding. The pole shoe has the wider surface. Its purpose is to spread the magnetic flux uniformly throughout the air gap. Why this is necessary? If the magnetic field is concentrated only at one point, the armature conductor will not receive equal magnetic flux. This leads an uneven torque and poor machine performance. Therefore, the pole shoe helps distribute the magnetic field evenly. Next one is the field winding. The field winding is made up of insulated copper conductors wound rounded on pole core. When we supply DC current to that winding, it behaves like an electromagnet. According to the electromagnetic principle, whenever a current flow through a conductor, a magnetic field produced around it. This magnetic field is essential to because without magnetic flux, neither motor nor generator can operate. So we can say that the field winding creates a magnetic field required for the operation of a DC machine. And next one is armature core. The armature core is rotating part of the machine. It is wounded on the shaft and rotates inside the magnetic field produced by the field poles. The armature core has slots. It's on its outer surface. These slots accommodate the armature winding. In each slot, the core is made up of laminated silicon steel insulated of a solid iron block. Do you know why? If we use a solid core, large eddy current losses will be produced. To reduce these losses, thin laminated sheets are used. This improves efficiency of produced EMF and also reduces the heating. And next one is armature winding, which is placed inside that armature core slots. Inside of this armature winding, they have been weighted with the insulated copper conductors. In a DC generator, these conductors cuts the magnetic field and generates EMF. In DC motor, these conductors produces a force and torque. Therefore, the armature winding in actual working part of the machine. And next one is a commutator. Here, the commutator can use it to convert the generated DC into AC, which converts alternating current into direct current. Many students get confused about this function. Let's understand clearly. Inside an armature, induced voltage is actually alternating in nature. However, we require DC output. The commutator acts as a mechanical rectifier. It converts the eternally generated alternating voltage into direct voltage. In this case of a motor, the commutator reverses the current direction at the proper instant. So the developed torque always remains in the same direction. Without this commutator, continuous rotation would not be possible. And the next one is brushes. These brushes are usually made up of carbon or graphite. Since the armature rotates continuously, we can't directly connect two wires to it. Therefore, brushes provide sliding electrical contact between the stationary circuit to the rotating commutator. They continuously collect or supply current during the rotation. Finally, we have the bearings, which are provides support to the rotating shaft and reduces the friction. This allows armature to rotate smoothly with the minimum mechanical losses. Generally, ball bearings are used because they have longer life and requires less maintenance. So now that we know all the parts of DC machine, let's understand how these parts work together to produce rotation. The working principle of a DC motor is based on Lorentz force. It states that whenever a current carrying conductor placed inside a magnetic field, it experiences a mechanical force. So, if you consider a north pole and south pole, the flux direction is definitely from north to south. If you consider north pole at the bottom point and south pole as at top point, the flux direction will be down to upwards. So if you consider a current carrying conductor which having a magnetic field around it when it allows a current flowing through it. Therefore, this current carrying conductor placed in this magnetic field, then the resultant will cause like this. And these conductor having two sides, which one is A side and B side. Here at A side, the flux direction around the conductor is upward. Similarly, the field flux is also from down to upwards. Due to this, the addition of flux is happened here at A side. Therefore, the stronger magnetic field has been appeared at A side, and at B side, a weaker magnetic field will be happened due to having opposite force appeared, and the resultant magnetic flux will be reduced. Therefore, the direction of a force from stronger field to weaker field will be happen. So let's understand in a sequence. Initially, a DC supply is given to the winding from external point. So it produces a stationary magnetic field between both the poles. At the same time, current flows through the armature winding. Now the armature conductors will carry through their arms, which are placed in a magnetic field. According to Fleming's left-hand rule, each conductor experiences a force. The conductors on opposite side experiences force in opposite direction. These forces together produces a torque. This torque causes the armature to rotate continuously. This electrical energy supplied to the motor is converted into mechanical energy. Now let's see how the same machine works as a generator. Here the process is exactly opposite. Instead of supplying electrical energy, we rotate the armature using a prime mover such as turbine or diesel engine. As the armature rotates, its conductor cuts the magnetic field formed by the field magnets. According to Faraday's laws of electromagnetic induction, whenever a conductor cuts the magnetic field, an EMF induced in it. So if you consider these working positions, if you go with the at position 1, the conductors move parallel to the magnetic field since they do not cut the flux. The induced EMF is 0 at this position. As the conductor moves to position 2, it begins cutting the magnetic field in certain angle. It produces a small induced EMF, which can be presented in this graph. At position 3, the conductors move perpendicular to the magnetic field produced by the field magnets. Therefore, the induced EMF reaches to its maximum value. Then, beyond this point, the position 4, the angle decreases again. So, the induced EMF gradually decreases, which has been presented here. At position 5, the conductors once again move parallel to the magnetic field produced by field magnets. Then the resultant is 0 EMF, so which has been presented here. As the rotation continues to position 6, the conductors passes under the opposite magnetic pole. This reverses the direction of the induced EMF. So the negative sequence will start from here. And finally, at position 7, the conductors again cuts the magnetic field at 90-degree displacement, producing the maximum EMF in the opposite direction. So, which is presented here. This cycle repeats continuously as armature rotates. Although the induced EMF inside the armature is alternating in nature, the commutator converts it into unidirectional output, giving a DC voltage at the terminals. So, in this today lecture, we have learned the construction of DC machine, the function of every important part, the working principle of DC motor, and as well as DC generator based on Faraday's laws of electromagnetic induction. In this next lecture, we will discuss the EMF equations of a DC generator followed by the construction and working principle of single phase transformer. If the lecture helped you understand the concepts better, don't forget to like the video and subscribe to Electric Concepts by PAVP and share it with your classmates. Thank you.